Jamie,
Matt,
I'm round your flat.
we have just recorded podcast 19 with a very exciting guest. Who was it?
It was with a chap called Jonathan McDowell, an astrophysicist from the Harvard-Smithsonian Center for Astrophysics.
Yeah, he knows his stuff.
He knows his stuff.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts, here in London, Matthew Russell and Jamie Franklin.
The Interplanetary Podcast.
Putting the ace
back into space. Quasar. Oh, we're going to be talking about quasars. The Chandra X-Ray Telescope.
We're going to learn a bit more about it.
Remember we were talking about the three different types of NASA space mission?
Yes.
Chandra is a flagship mission, so it's one of the big ticket things, and it's regarded as one of the great observatories. It's one of the big important telescopes in the world, along with Hubble and Spitzer. This thing is genius, named after Subramanian Chandrasekhar,
Right.
who was a Nobel Prize winning astrophysicist, and he's also the nephew of another Nobel Prize-winning physicist, and he did a lot of work on stars and star formation. How did Chandra get into space, do you know?
I don't know. Tell me, Matt.
It went on board a space shuttle, the space shuttle that was being commanded by the first female commander, Miss Eileen M. Collins, who'd been into space 3 times already.
Come on, Eileen.
Yes. So I've got to tell this story because I think it's really weird. On that space shuttle flight, there was some gold coins. It's so weird. So these gold coins had been struck as a sort of example of the 2000 Sackaway dollar in June 1999. So it was obviously some kind of millennial dollar thing that they had going on. 27 were melted down out of the 39 that was stamped, but 12 went on board the shuttle Columbia.
Why?
I don't really know why, but presumably for some form of coins that have been into space.
Well, just in case if you pass like a petrol station that doesn't take card.
Yeah, you just go, I've got
How about this melted down gold coin?
I've got this gold dollar that's been in space.
Oh, they're accepted everywhere.
Well, it turns out that they're not, because it was illegal to even stamp these things because it went against the thing. So they were transferred to Fort Knox, and it took until 2007 before they were publicly displayed as space-flown gold dollars. So weird.
So that's almost like a space pirate.
Your favourite event, I hear, the World Fair of Money in Milwaukee.
Oh, I love that place.
I know you love it. So, without any further ado, we're joined by Jonathan McDowell on the Interplanetary Podcast. He is an astrophysicist from the Harvard-Smithsonian Center for Astrophysics. And I believe one of your main concentrations is on the Chandra X-Ray Telescope. Is that correct?
That's correct, yes. Pleasure to be here.
Can you tell us a little bit about X-Ray astronomy?
Right, well, first let's talk about what X-rays are, because, a lot of people, everyone's had X-rays at the dentists, but often, you don't have really clear idea of what they are. They're just another color of light that our eyes can't see. And just like ultraviolet light as ultraviolet light is to blue, as blue is to red, X-rays are to ultraviolet. They're even more badass ultraviolet. And so just like ultraviolet rays give you a tan if you sit under a UV lamp, X-rays go even deeper into you. They pack more of a punch, and so you don't want to be exposed to too many of them. So how do you make X-rays? You make them when things get really hot or when they get radioactive. And so, for example, if you have gas at 1,000,000 degrees, it's not red hot, it's not white hot, it's not even ultraviolet hot, it's X-ray hot. And it glows like crazy in X-rays, but it's completely transparent in ordinary light. So if you look at a nebula, an exploding star that's at 1,000,000 degrees, you won't see it at all with a telescope like the Hubble. You'll see right through it. But if you take an X-ray telescope like Chandra and look at it, you see this really bright, glowing thing. So it's a really good way of finding out where the extreme objects in the universe are. So the way we think of it on Chandra is, Hubble sees the ordinary stars, and we see the places where the universe is going seriously wrong.
So what's the difference really between X-rays and gamma rays?
The gamma rays are the next step out. They're even more extreme than X-rays. And so, they're good too, but the further out you get, the fewer of them nature tends to make. And so gamma rays are quite hard to catch. There aren't as many of them. And our telescopes that detect gamma rays, they have to be really heavy, and we can't afford to build a big one yet. So X-rays are sort of in that sweet spot where we have the technology now to get to study them, and they tend to be made by a lot of really interesting objects. And so these X-rays, like a quasar that we're going to talk about in a little bit, 1 billion light years away, the light, including the X-ray light, crosses the universe for 1 billion years and reaches the Earth, and then the X-rays get stopped by the Earth's atmosphere after all that time. They can't make that last half second. And so by putting our telescope just above the atmosphere, we can suddenly see all the stuff that we can't see down on the ground. Which is, to be fair, it's probably good for us that the atmosphere stops all the X-rays coming in. I mean, it's annoying for X-ray astronomers, but it would be kind of stuff for everybody else. So so putting our telescopes just that little bit above the atmosphere, it's sort of like, when you're swimming in a pool underwater and you can't see very far, and then you surface, and suddenly you can see a much bigger distance in the air. It's like that. We're swimming around in this murky atmosphere, can't see very much, pop your head above the atmosphere, and suddenly you can see clearly.
And Jonathan, you've mentioned the Hubble telescope, and why do you think there's not as much press about the Chandra as there is the Hubble? And do you think it deserves to be more in the public imagination?
I absolutely think it deserves to be better known. There are a couple of reasons why. One of them is because there are fewer X-rays. In a sense, the things that are shining in X-rays are fainter.
Right.
And our telescope isn't that big. And so all of our pictures that we take with Chandra tend to be, by normal standards, a bit underexposed.
Right.
We tend to take just enough data to get the science answer we want, and you'd need to sort of expose for 10 times longer to get the really pretty picture that would blow people's minds.
Sure.
And so we do have some amazing pictures, and chandra.harvard.edu, you can go find all our amazing stuff. But Hubble does have an advantage there. Then we also, we have a couple of people working on PR for Chandra. They have an entire wing of the Space Telescope Institute, so they got a lead there too.
Yeah, sure.
I mean, one of the pictures that's always quite enjoyable are the ones where they've combined quite a lot of the different telescopes' images to make one super image. And one image that I think is particularly strong, which is Chandra and Hubble, is the image of Tycho that I'll put on the notes for the podcast. Can you tell us a little bit more about that image? Because it seems very, very interesting.
Right. And in general, let's say that's really the thing to do, is to use all the different wavelengths, all the different colors of light. Because if you just use visible light, you've just used the Hubble, for example, it's sort of as if you were walking around town and you could only see things that were colored green, and everything that was colored blue or red was invisible to you. So you really need to put them all together to get the full picture of what's going on. Now, the Tycho image, which is mostly Chandra, is that's really a fun one, because if you plot up what you can see with visible light, really there's nothing there, there's just stars. And then if you switch over to the X-ray, there's this enormous exploding sphere. And we've now taken a number of pictures of the Tycho supernova remnant. So let me just say, the original discovery of this, there was a Danish astronomer called Tycho Brahe, so really should be Tycho, who saw this new star in the sky in the 1570s. And you could see it with the naked eye, and it slowly faded away. And there's nothing there now, except if you look in X-rays, and you can now see this cloud that's several light years across, right? It's much bigger than the solar system. And when you take pictures of it 10 years apart, it's gotten slightly bigger. We actually have a movie showing it expanding slightly. And so we can measure how fast it's expanding. If you run that movie backwards and ask, when would that all have been at a point? Sure enough, in the 1570s.
Wow.
And so we're seeing the explosion still underway, but the gas is so hot that it's shining in X-rays instead of ordinary light.
Wow.
That's mind-blowing.
And if you look at it carefully, you can see there's an outer sort of bluish spherical part, and then there's all this kind of almost cotton wool kind of clouds inside. And so the bluish part is the shock wave passing through the thin gas between the stars and lighting it up. And then the cotton woolly stuff is the debris from the explosion, the freshly made elements that are following on close behind. And so, we're all made of stardust, right? Everyone knows that. And with Chandra, we can study the freshly made elements that are the new stardust that is eventually going to coalesce into the next generation of stars and planets, just like we were made the Earth was made from the atoms of an explosion like that.
Wow, that's amazing, isn't it? I mean, with the Tycho explosion, was there any remnant left at the centre? Did it leave a black hole or anything like that, or is it just literally the expanding gas that we're left with?
There probably is a remnant in the middle, and whether it's a neutron star or a black hole, I'm not sure. I don't remember the details with Tycho. There's another remnant called Cassiopeia A, where Chandra has spotted for the first time the neutron star that's in the middle of the remnant that's left over. And there's a bunch of remnants where we do see the leftover thing, and there's somewhere we don't. And it's just a question whether they're glowing appropriately or not.
So, Jonathan, do you know what the nearest and the furthest quasar detected is?
Well, that's an interesting one. We've got to talk a little bit about what a quasar is, right?
Yeah, that's a good start.
So it turns out that you and I live on a planet which is going around a star, and that star, the sun, is one of many suns in a galaxy of stars. But we used to think, okay, that's what a galaxy is. A galaxy is a bunch of stars. Some of them might have planets. It turns out that another thing a galaxy has is whopping big, enormous black holes.
Yeah.
And they're ordinary black holes, the ones that when a star a little bigger than the sun blows up, it might leave a black hole behind. And they're maybe, a few times as heavy as our sun. But in the middle of the galaxy, and in the middle of almost every galaxy, there is one whopper black hole, what we call a supermassive black hole. And our galaxy has one that's kind of below average. It's only about 10 million times the mass of the sun.
Right.
Yeah.
Some of them are up to 10 billion times the mass of the sun.
Wow.
And so you've got this big thing as the nucleus of the galaxy. And it can just sit there in our galaxy. The black hole, it doesn't seem to be doing very much at the moment. Occasionally we see a burst of X-rays as it rips apart an asteroid and chomps down on it. But it's mostly dim. Whereas in some galaxies, one of the nearest is a galaxy called Centaurus A, also known to its friends as NGC 5128, because we are so poetic in astronomy.
Yeah, rolls off the tongue.
And this object has a black hole in the middle that matter is falling into, and once it falls into the black hole, you can't see it, of course, but on the way in, the gravity of the black hole kind of rips it apart, makes it glow, makes it really hot, puts out lots of X-rays, and lots of visible light, puts out every kind of light. And that's what we call a quasar. It's a black hole in the center of a galaxy that's swallowing stuff and making the stuff glow. Right. And some quasars, like the one in 5128, the black hole is spinning, and it's eating stuff that's falling in along its equator, but it's gathering stuff from a region around it, and that the stuff that's falling in from further away, it isn't aimed quite right at the black hole, so it sort of all accumulates in a disk around the black hole's equator, and some of it doesn't manage to go down the black hole. It gets caught in the magnetic field and shot out the north and south pole directions at almost the speed of light, and so you get these remarkable jets that come out. So about 10% of quasars we see have these enormous jets of material where you take the mass of the Earth every year and accelerate it to the speed of light, and these jets blast through the galaxy that they're sitting in. So that's quite a spectacular thing. So in general, the quasars, let me tell you how bright a quasar is. Our sun is, all the energy that we use on Earth, right, fossil fuels and so on, with the exception of nuclear energy, comes ultimately from our sun.
Yeah.
Our sun has been shining for 5 billion years. It's going to shine for another 5 billion. We intercept a tiny fraction of that energy. It operates by the famous equation, E equals mc squared. It turns about 0.1% of its matter into energy over 10 billion years. And that tiny fraction of its matter, E equals mc squareding into energy, is enough to power the sun for 10 billion years. One of these quasars takes the entire mass of the sun and turns it into energy every year.
Okay.
So you don't want to sit next to one of these things.
Definitely
that
not.
Means we can see them a very long way away, and so we can study them all across the universe, and they're particularly easy to spot with X-ray telescopes, because although they put out ordinary light, if you have a quasar a billion light years away shining enormously in ordinary light, and a star a few hundred light years away also shining in ordinary light, in a picture, they don't look much different. They just look like dots. But the star won't be putting out a lot of X-rays, whereas the quasar will. And so if you take an X-ray picture where you would have 1 million ordinary stars and one quasar hiding among them, in the X-ray picture, you just see the one quasar. Oh, there it is, done. And so we've now made a catalog of over 100,000 of these quasars with black holes in them.
Right.
All through the universe.
So
Chandra's a great machine for finding that.
Are most of the quasars from a sort of earlier period of the universe's formation?
The bright ones are, yes. And what happened is, in the early period after the Big Bang, when the galaxies had just formed, there was a lot of free gas around for the quasars to chomp down on. Mm-hmm. A lot of that now is locked up in stars. And the galaxies are further apart from each other, so they don't bump into each other as much. So there are a number of reasons, we don't really understand them all well yet, why quasars were more numerous and brighter in the early periods of the universe after the Big Bang, the first billion or couple billion years after the Big Bang. And so a lot of what I study is the period of the universe before the Earth was even formed. But having said that, there are less luminous quasars all over the place today, and so a lot of these nearby galaxies have some level of activity. Their black holes are still there. They're kind of dormant. Some of them are glowing enough that we can call them quasars, or at least active galactic nuclei, AGN, which is sort of the more umbrella term that includes things that are kind of wimpy quasars. And so it's a phenomenon that's actually really important. So the energy for these things is coming from gravity, really, right? It's like the matter settling into the gravity of the black hole, converting the energy of that gravity into light. And it's quite different from the light from stars, which comes from nuclear fusion. So when we look up in the sky in the visible light, most of the light you see is coming from nuclear fusion in stars. But in the X-ray band, what you're seeing are these gravity reactors that are turning gravitational energy into light, and so the universe is sort of a more complicated place than we thought when I was in school.
Absolutely. Wow. And Jonathan, how does the angle of view affect things?
Right. So one of the problems with quasars is stars are nice because stars are sort of round. Quasars are not. They have jets coming out the poles. They have an equator, and so what you see depends on what angle you look at them from.
Sure.
And in particular, if you look right down the jet, if you're lucky, and of course you can't choose, right, because these things are billions of light years away. It'd be a long trip to go and look around the other side of
yeah.
it. But if you take 100 of them, some of them are going to be, you're going to see them from the side. Some of them you're going to see them from the top. 1 in 100 you'll see looking right down the poles. And if it's one of the ones that has one of these relativistic jets, these jets of material coming out at the speed of light, you'll see all kinds of truly weird effects due to relativity.
Sure.
And those are the ones that we call blazars.
Right. And are they dangerous?
Well, all of these things are dangerous if you go too close to them.
Sure.
And in particular, what I would say is there's one of the things we worry about is if all galaxies have these things in them and some fraction are active, is it that all of them are active some fraction of the time? And if so, could our galaxy become active one day? And could we get a really serious bright quasar or blazar in the middle of our own galaxy, which might be bad for the real estate values around here?
Yes.
That's one of the research questions we'd like to answer. I think the balance of the evidence is it's unlikely we'll have a really major quasar appear in our galaxy in the future, but we might have a minor event. And indeed, in the past couple of years, one of the gamma-ray astronomy satellites called Fermi discovered what are called the Fermi bubbles, which seem to be the leftover in our galaxy, leftover gas from an earlier eruption of our central black hole.
Whoa.
And so that could be, that could be the sort of thing that if it went in the wrong direction, if we were in its path, that could be a mass extinction at least, perhaps. People haven't really understand well enough to know what the effects would be if you were right in the path.
Yeah, it's a good job the universe isn't retracting, that's for sure.
So, I mean, even though we're kind of in the galactic disk, aren't we? We're not. So these poles can fire out in any direction, or is it, or are the poles of the central black hole actually aligned with the disk as well?
Not necessarily. We don't know where our black hole is aligned right now. I think it based on the evidence of the Fermi bubbles, it's not pointing at us, so that's good news. But stay tuned. It's still a bit of a work in progress.
Well, not much we can do about it, presumably, if it happens.
No. Duck and cover.
So, Jonathan, we know that you've got an asteroid named after you, which is ridiculously exciting. Can you tell us about that?
Well, it's a little rock about a mile across, so it's called a minor planet, but it's really very minor. It's minor planet number 4,589, and it's in the main asteroid belt between Mars and Jupiter. I have actually observed it. I took a picture of it a number of years ago, just as a dot going across the sky. And it's the Minor Planet Center in here at the Harvard Smithsonian does have the naming rights to the sort of leftover asteroids that no one else has named.
Sure.
So this asteroid was discovered in the 1930s. The guy who discovered it, it wasn't sort of confirmed until after the guy who discovered it had died, and so the naming rights reverted to Minor Planet Center. And I helped them out on a number of studies of putative asteroids that turned out actually to be space junk. And
got it.
So they honored me with it. It's very nice. But yes, so I work with them occasionally, although my main interest is in quasars. I also have an interest in asteroids, and there are a few people here at the Center for Astrophysics, like Martin Elvis, who are really interested in the possibility of asteroid mining.
Yes, we discussed that a few podcasts ago.
Right, exactly. So we're really looking at what surveys do you need to do in order to find the mineable asteroids and stuff? And then as we're probably going to mention, I'm interested in space junk of various kinds. And so just occasionally, the astronomers discover an asteroid, and it's in an odd orbit, and then they see it maneuver. And then they come to me and I go, oh yeah, okay, no, you've just rediscovered this space probe that's not really an asteroid.
Yeah.
So I try and keep track of that stuff for them.
Sure. Well, yeah, there's as we discussed this a couple of podcasts ago, there's quite a lot of space junk, isn't there? Frighteningly so.
Yes, there is, and it's starting to be a real problem. It's just like the sea, right? You go, oh, space is big, we can dump as much junk as we like in there because it'll never fill up. And then, 20, 30 years later, oops.
Yeah.
Because the trouble is that this junk moves at, 7 kilometers a second. So if you take an instantaneous snapshot of near-Earth space, you'll just see a lot of tiny dots on mostly empty space. But if you take a 5-second exposure snapshot, each of those dots will be 100 kilometers long.
Yeah.
Suddenly it doesn't look as empty as it used to.
Yeah, I mean, when we were discussing it, we realised that it's such a hard problem to solve, isn't it? You've got because these things are travelling around so fast, and they're things like spatulas dropped by Piers Sellers and things like that. And
that was re-entered long ago, but yeah.
Yeah, but it's little flecks of paint and all those sort of things. You think actually, this is it's how do you get them down? I actually one method that we didn't mention on the podcast last time, which I saw coming up quite recently in a feed, is lasers on the International Space Station.
I haven't read about using them on ISS, but you could use them on from the ground to zap the smaller pieces of debris. The thing about that is, the studies people have done suggest that it's actually the biggest pieces of debris that are the big problem.
Yeah.
In that you get the kind of Kessler syndrome runaway of turning Earth into Saturn's rings. When the big satellites hit each other, and that's actually an easier problem to solve with space garbage trucks and so on. And I think all we need to do is put a tax on satellite operators to fund a fleet of garbage trucks, and that sort out the problem pretty well. But it's just got to get to the point where the people who are making money out of space get sufficiently worried about it that they actually agree to do something about it.
Yeah, absolutely. We discussed the big one for the Europeans was trying to remove Envisat, which they're going to have a little go at, aren't they? With E.D orbit, I think is the name of the project that ESA are doing. But that should. That's some. A lot of these plans are quite a long way off. We're looking at 2022 or something for that particular mission.
Yeah, and I think the important thing in the short term is to minimize the amount of new junk you add, and the occasional satellite that you can't get down is not a big deal, but you don't want to be launching lots of them that are going to be littering. So people are doing better. 20 years ago, most satellites didn't even have propulsion systems, so they just had to re-enter naturally. And now most of them do have some way of getting down. There's a couple of interesting experiments just jettisoned from the space station last week, which have various kinds of deployable sail. These are little CubeSats that they deploy sails to increase their friction with the atmosphere and make them re-enter more quickly.
Yeah.
So, Jonathan, we know that you've got your own space blog. Can you tell us about that and where people can go to read it?
Right, this is Jonathan Space Report. So if you Google that, you'll find it, and it's at planet4589.org. And I started this really back in 1989. So that was before the World Wide Web. It was on FTP and on Usenet, and really it started because the public affairs people at the observatory kept getting queries from the public about space and satellites that they didn't know how to answer, and so I started preparing them a weekly brief on things they might get questions on.
Right.
And someone said, well, you should put this on the internet because people will like it. And I went, no one will be interested. But surprisingly, it turns out that people are. So I've now done over 700 issues in over a quarter of a century. So it's one of the longest running internet newsletters.
You've become the Patrick Moore of space blogs.
That's a nice idea. It's really sort of mostly aimed at the true space geek who has at least heard the word sun synchronous orbit or something like that. But I try and cast it so that the layperson can get something decent out of it. And really, I'm trying to be the journal of record. If you launch a satellite, I'm going to mention it.
Yeah, I mean it's been a fantastic resource for us because I'm always referring to it for what we're going to talk about on the show.
Right, exactly. Well, it started off. I when I was a teenager in Surrey, I was, of course, the British press weren't very good at space news, and so I was frustrated at the lack of space journalism that I could access, and so I learned to do my own research and started making lists of satellite launches, and I found a list in the back of James All the World's aircraft in the local public library, and then I pretty soon realized that it wasn't the best list you could do. And so I set off in my obsessive way to make a better list, and now, 30, 40 years later, I feel like I have a decent list. So, so that's sort of how it starts, is like, it doesn't matter what you obsess about, but obsess about something, and it's not, if you're narrow enough in it, you can become world ranked pretty quickly.
Yeah,
there's hope for us yet, Matt. There's hope for us yet.
It's quite funny. Yeah, my eldest son's just about to become a teenager in Surrey, so perhaps he'll take note.
Well, hopefully there's more sources of space news now, though. You see, that's what the internet's been great for.
Yeah, I mean it's surprising. I'm always amazed by how little space news there really is when you compare it. If you walk into a magazine shop, I don't know what it's like in America, but if you walk into a magazine shop in this country, right, you see maybe 20 magazines on yachts, 4,000 magazines on fitness and health, and no magazines on space flight. You're lucky if you. I mean, are you still a member of the British Interplanetary Society? Is that correct?
I am, yes, since 1976, and you do occasionally see space flight. For a while, Spaceflight were putting their stuff in W.H. Smith's, I think. Yeah. But yeah, it is hard to find. And so, yeah, I discovered the BIS as a teenager and would go up to meetings in London, particularly the Soviet Space Forum, which was really, really fun in those days. And so that was great to get connected to some older people who are more experienced in how to do analysis, Phil Clark and Jeff Perry and so on, who were really the pioneers of this sort of space nerdery.
Yeah. Fantastic. So was that up at Arthur C. Clarke House on your day, or was it somewhere else?
Let's see. When I first went, it was Bessington Gardens. I think it was some small place, and then they did a big fundraiser and built the place on South Lambeth Road in Vauxhall. Is that?
Yep. That's Arthur C. Clarke House.
That was not called that in my day, but yes, I remember when that opened. And so yeah, that was really much, and it was always good because I don't know if this is the case. It was in the Bessington Gardens days. It was you got a cab there. Mm-hmm. And the cab driver go, oh yeah, I know that, because it was one of the things on the London cabbie test exam.
Yeah, apparently still is. Yeah. So yeah. One thing that we always do at the end of our podcast is to have the news, what's happened in the week, because it's a weekly podcast, and what launches are coming up. And being that we've got an expert, what exciting happened in the news for you this week in space?
Ooh. Well, let's see. This week, there was the launch of Japan's been very active recently. Mm-hmm. They just launched their first military communications satellite. They've also deployed, as I mentioned, a bunch of CubeSats mm-hmm. from the space station with these drag devices, not this. I don't know if you covered in earlier weeks the launch of the little rocket, the SS-520, that was trying to put a single CubeSat in orbit, but it failed, which is unfortunate. But that was an interesting attempt. So it's been interesting to see Japan being both very active and very innovative.
Mm. Well, they tried that tether experiment as well, didn't they, recently, for the space
the tether
jump
experiment, which, as far as I can tell, didn't work, but I haven't been able to confirm that. I tried emailing them, but they didn't reply. We also had the launch of an American early warning satellite, and that's a big, high price, big mission. It's the third in the series, and it's the thing that sits in geostationary orbit, and if you launch a Scud missile, it'll spot it.
Uh-huh. That was on an Atlas V, is that right?
That was on an Atlas V, that's
Yeah.
right. And meanwhile, in deeper space, OSIRIS-REx, which is the asteroid sample return mission, just made a little orbit course correction that's put it properly on course for an Earth flyby later in the year. So it's doing one of these fun space ballet things, right, where it whizzes past Earth a couple of times to pick up speed, and in order to send it out towards this asteroid that it's trying to return a sample. Bennu, that's right, yes.
So did you see the picture that NASA released from the GOES 16 satellite? Because that
with the moon.
Yeah, with the moon. With the extra super ace resolution of the Earth. I thought that was
that's right.
Nice touch.
And this new generation of weather satellites, and again, actually, it was the Japanese who launched the first one with this technology. Their Himawari 8 is very similar to the GOES 16 that took this picture. And so we're moving into a newer generation of higher resolution and higher cadence, meaning you take the pictures more often. And that technology is also being used on the astronomy side. We have a spacecraft in geostationary orbit turned around looking the other way at the sun, taking high-def video of the sun. If you Google Solar Dynamics Observatory, you'll find some very nice videos of weird things happening on the sun.
Yeah,
very nice. I'll have to check that out.
That'd be worth it. Yeah, so I think, we're the early part of the year in space activities tends to be a little quieter because everyone's been off on holiday. The Chinese were launching an awful lot of stuff in December and the beginning of January, and they're now repainting their launch pads and things. So,
right. I've heard one piece of very exciting news today on my way over, and that's that Tim Peake, the UK astronaut, has actually been officially got a second mission to the ISS.
Oh, that's very exciting! Congratulations to him. Yeah,
and because he's been unveiling the Soyuz capsule that is now on display at the Science Museum. So he unveiled that today, and they announced that while he was unveiling it. So that was quite a touch.
That's good, and hopefully it won't be too long before we're not just using Soyuz, we're also using Dragon. Yeah. And on that note, the next Falcon 9 launch has just slipped to February. But because they haven't got the launch pad ready yet. And this is sort of worth paying attention to, that we kind of toasted the launch pad on the East Coast last year. So the Falcon 9 that flew the other week was from the West Coast, from Vandenberg Air Force Base. And the next East Coast launch is going to be from Pad 39A, which long-time space enthusiasts will remember as Apollo 11's launch pad and the shuttle launch pad. And so that's been refurbished for use with the Falcon Heavy, but also with Falcon 9. And so we'll see a Falcon 9 from Pad 39A probably in the next few weeks. And so I think that's going to be very exciting.
And they're not going to be reusable ones, are they, these ones? They're expendable rockets. Is that correct?
This next launch is expendable. And that's just because the performance you need to put this satellite in geostationary transfer orbit, it's a bit too sporty to try and bring it back. There's not enough leftover fuel.
Yeah.
And so as they further roll out, Elon Musk has just talked about the Block 5 of Falcon 9, which is going to have even more power and will therefore have a little bit more leftover fuel, and so even for a mission like that, it might be able to use a reusable first stage. They've also started to put on the schedule the SES-10 satellite that's just arrived in Florida. That's for a globalized company called SES, which is based in Luxembourg, a big communication satellite, and they're going to be the first commercial passenger, first passenger of any kind, to ride a previously owned Falcon 9 first stage.
Wow, that's going to be very exciting, isn't it?
Yeah.
Incredible.
That's the real test of reusability. It's not just landing the darn thing.
Yeah.
It's putting a fresh coat of paint on it and firing it again. And they haven't done that yet, but that's coming up. So that's super exciting. I mean, we've mentioned it on the show before. Is that obviously the couple of mishaps that the Falcon had has set back SpaceX a bit. But one of the things that worries me is that they're not fulfilling, like you said, these commercial missions for non-commercial missions for getting crew up to the International Space Station, because that's slipped back now, isn't it, to 2018? And there's been talk of having to book more Soyuz seats. That's right. I mean, I'm actually more worried about the commercial ones, because the commercial ones have other options. Whereas, what are NASA going to do? So I think that NASA will just be patient and wait till things are ready. They're not on a commercial, they're not going to care about losing money, right? Yeah. Whereas if there's too many delays to the communication satellite launches, the customers will just go on Ariane.
Yeah, that's true.
So I think that for human spaceflight missions, the watchword is slow and steady.
Yeah.
Much rather have it slip another 6 months than have one fail.
Yeah,
and
what do you think with the Trump administration? Do you think that he doesn't seem the kind of guy that has much patience for people using the American taxpayers' money? Do you think that will? Do you think Musk? Do you think that will affect Musk and SpaceX?
Well, I've been very careful what I say here. So let me just say, what I do notice is that Musk has been in more than one meeting with Trump.
Mm-hmm.
So he at least has Trump's attention.
Yeah, in fact, I read today that he wanted to keep the lines of communication open. He said that was more important than attacking Trump because it doesn't seem to do any it doesn't seem to make any difference when people do. So I think he knows what he's doing.
Yeah, so I feel like I should stay out of the political discussion. And we live in interesting times.
And Jonathan, are there any launches happening in the next several days?
Yes, is the answer. Oh, that's right. It's on the Soyuz from Kourou. So this is kind of interesting because it's the first commercial launch on one of these Europeanized Soyuzes to geostationary orbit. And that's right. And this is a satellite, communications satellite that's been actually long delayed and long awaited for by a small European company in Bremen, Germany called OHB.
Yeah.
And they have a new geostationary satellite bus, and they've built a satellite for a company called Hispasat, which is a Spanish telecommunications provider. Okay. And so the satellites like that would normally go up as one of two passengers on an Ariane, or maybe go up on a Proton from Russia. But instead, this one's going to go up on a Soyuz with a frigate upper stage from the jungles of French Guiana from the Kourou Sinomari launch site. And so that's a test of Arianespace's commercialization of the Soyuz as a smaller alternative to Ariane.
Right. And
so with the, shall we say, checkered history of recent Russian launch.
Yeah.
It's going to be interesting to see. The failure report, by the way, for the Progress flight that failed last December is out now. And there's been a big kerfuffle.
Well, someone's resigned, haven't they, from the engine manufacturers?
Yeah, so the Voronezh Mashinostroyenie Zavod, the engine manufacturing plant in Voronezh, is in big trouble because they've been implicated in several failures, and the claim is that their quality control is crap, to use a technical term.
So they've been using cheaper metals, haven't they, instead of the correct
that's
alloys?
The accusation. They have to be a little careful because there is a tradition in Russia of finding the scapegoat to blame. More so that the West has had a more open, blamey kind of accident investigation process, and so one does, you can't be certain, but it does look like they're implicated in this. And so there are two main engine manufacturers in Russia, Energomash, and which made the original rocket engines for Soyuz and so on, and they make the RD-180 that powers the Atlas in the U.S. And then Kiev Avtomatiki, which is this Voronezh company, and they've made engines for the Proton rocket in the past, for example. And so this may mean that they get in more trouble, and the Energomash people get even more business than they're already getting.
Yeah, I mean, it looks like there's not going to be a Proton launch for a long time now as well. So that's been put back again.
That's right. It's they've got to do some real quality control scrubbing, I think, to make sure that they don't lose another one. And really, this has been a problem kind of since the fall of the Soviet Union, is quality control, and particularly in the subcontractor chain. Like you may be careful still at the aerospace company, but if you buy a widget from some other Russian company that hasn't been doing too well in the post-Soviet economy, that sort of chains on. So that's kind of an endemic problem in the Russian space program right now. It's really noticeable. I did my usual end-of-year statistical summary for space, and for the first time, China's overtaken Russia in the number of launches, and the number of Russian launches has really dropped. Has been slowly dropping for a couple of years, and so after a period of decades when Russia was by far the most active launcher of satellites, partly because their satellites crapped out after 2 weeks, so they had to keep launching them. But still, they had really good rockets and really knew how to do it, and just with budget cutbacks and so on and so forth, you can see the Russian program shrinking now. And maybe that's just temporary, but it's really noticeable.
Yeah, well, it was the first year that America actually launched more than Russia last year, wasn't it? 2016. Is that correct?
Since 19. Actually, that's not true. There was a dip after the fall of the Soviet Union in the mid 1990s, when America did that again, and there was up until 1965, America was ahead of Russia, but there was a long period of decades where Russia would launch many more rockets than the US.
Yeah. I mean, I noticed that the ones that fly out of Kourou are ticked down as Russian launches, but I always think that.
I don't. I mean, I've been counting them in the last few years. I've been counting them as European launches, but and they're certainly. I think the upper stage, for example, would be registered with the UN by Arianespace. But on the other hand, it's I'm sure that at the launch site in French Guiana, there's a bunch of Russian engineers who are actually doing the work.
Yeah.
So
absolutely.
Whether you count those that count French Guiana Soyuz as a European rocket or a Russian rocket, it gets really hard. And this is part of a bigger problem actually with the globalization of the space industry, is that so much of the discussion about space, and in particular space law, is based on nation states and on the assumption that it's, a country is responsible for what's happening. And as we move into an era where, a company like I just mentioned, SES, based in Luxembourg, but also has absorbed American companies and Asian companies, it's really globalized. What country are its satellites really? It's kind of hard to say.
Yeah.
And you get, I give the example of a South Korean satellite from a few years ago, which is owned by South Korea, built in France, and launched on a sea launch from international waters, which is a Ukrainian-built rocket with Russian engines and American marketing. And trying to lump things. And so then, journalists ask me, all right, how many satellites has X country launched this year? Well, it's not a well-defined question anymore.
No, absolutely not.
And so I think we have to recognize that, maybe we're moving into the era of the corporate citizenship, and the era of the nation state, and the Treaty of Westphalia is passing.
Thanks very much for joining us. We better start wrapping it up. Otherwise, our weekly podcast will be far too long. But that's been really, really interesting.
Absolutely.
There's loads more I'd have loved to have covered on.
Well, maybe we can go to it another time. Pleasure to chat with you guys.
Thank you very much, and have a lovely rest of your day and enjoy the rest of your meetings.
Likewise.
Thanks, Jonathan. That was really great. Cheers.
Cheers. Thank you. Bye.
Thanks, guys.
That was our interview with Jonathan McDowell, and we really, really, really enjoyed it. And so hopefully we'll have him back on the show very, very soon, because there were so many things that I'd like to talk about.
We left so much out. But we would love to make it into a series. What a lovely guy, and definitely check out his blog. And hopefully we'll make that into kind of a mini series.
And if you get a chance, check out a thing called the sound waves from the violent activity called the cosmic B flat. It's so low that it's 50. I love this. How many octaves is it? It's 57 octaves below the key in the middle of the piano. So 57 octaves below middle C.
I thought it sounds like a Norwegian metal band.
Yeah, that's definitely low. It's the lowest note ever recorded.
Wow.
Brilliant.
Well,
so look that up. So we need to talk about stuff like that. There's 1,000 things. Just so you know, Chandra went up, and it was only supposed to be a 5-year mission, and it's been out there working for 17 years and 6 months. Look on the blog. There's a picture of the hand of God. That's amazing.
It is ridiculous, and long may she continue.
So thanks very much for joining us, and remember, keep sending in brilliant questions. We had a question from last week's podcast about Saturn, one that I've really thoroughly enjoyed.
Oh yeah, what was it?
But the question was, why is it that if Saturn's only got 1.1 times the gravity of Earth, it has rings? So I was really trying to look into, why does Saturn have rings? It's actually quite hard to find out why Saturn has rings, and the only answer I could find is because God liked it so much he put a ring on it.
Oh, okay.
That's where that picture came from. But genuinely, I'm not quite sure. I thought it's because even though it's only got 1.1 times the gravity, it's huge. So therefore, its gravity well is big.
Absolutely,
it might be only a little bit deeper, but it's much, much bigger, so it must be something to do with that. So if any listener knows why that is, we should have asked.
We should have asked Jonathan.
Oh my gosh.
Jonathan, if you're listening, that's our next question.
Let us know. Why does Saturn have rings? Because I'd like to know.
I'd like to know. Who's that question from?
And that was from Justin Young.
Cheers, Justin. Sorry we can't give you the answer yet, but we will endeavour to get the answer.
Absolutely.
So,
thank you very much for listening. Don't forget to subscribe on iTunes and Stitcher, and to leave us a good review.
Leave us a nice review if you enjoyed yourself. If you didn't, then don't leave us a review.
Don't do one of those. What's it go when people stop it in hotels and TripAdvisor?
Oh, yeah.
Yeah, we might charge you, might fine you.
Yeah, exactly.
Yeah, you listen to this for free, you'll owe us a £5 if you give us a bad review.
But thanks very much to Jonathan again for allowing us to interview him.
So, me and Jamie are off to go and get beer now.
Here we go.
Cheers.